once you like realize that. So today, 15.3, we're getting into geometric sequences. But I bet you could figure this out really easy. Are both notes still up? So you have your arithmetic sequences from yesterday. If you compare your arithmetic sequences with arithmetic series, Megan?
Does series end?
Series have an end. So a series would be like you're looking at rows of seats at a concert. There is going to be a back row. Or if you're talking about, what's another real example we use? I mean, you could talk about stacks or like cups in a pyramid. And you can't have an infinitely large pyramid. So as you go, you're going to add 2 on each side. And so we then are able to sum a series because it ends. So that's the difference between sequence and series. We're not getting into series today. We will tomorrow, but today we're getting into geometric sequences. So just as with series, that ... on the end there tells you that it is going to go on forever and ever and ever. So just like arithmetic was adding to get to your next term, geometric is going to be multiplying or dividing, which is multiplication. So here in sequence A, what do you think the next term would be?
48.
48. How'd you figure that out, David?
Because they're all multiplying by 2 up to that point.
So the next term then?
96.
96. And the next term?
192.
192. Go ahead and fill in those next 2.
Did I get it right?
You did get it right. Good work, sir.
I'm smart in the pants. Are we going to finish the 15?
Wait, didn't we finish?
You did. Were you here at the beginning of class yesterday?
No, we're on 15.3 right now. She's asking if we didn't finish 15.2. No, we didn't finish.
I was thinking 15.1. Sorry, I heard you. I was just thinking something else. Did we not? Oh, yeah, we ran out of time because we got chatty.
Chatty. But that been
Go
inside
figure.
I think it's
Sorry, did you guys get in trouble for being late? Hopefully not.
No.
No, that's the same thing though. Miss Amir hates Brian's class because they don't stop talking.
So in B, while this loads, we'll go back to it.
Oh, yeah.
In B, while this loads,
Yes.
if B starts with a tenth, goes on to 100th, goes on to 1,000th, goes on to a 10,000th, what do you think the next one is? 100,000th, and then
A million.
a millionth, and then 1/10 millionth, and 100 millionth, and so on. Now C's weird. C is weird. Why is C weird, Michelle?
It's a negative number and it's also times a fraction.
So it's multiplying by a negative fraction, which means my terms are going to alternate negative, positive, negative, positive. What is that fraction between them, Calvin?
A negative third.
Negative third. So my next one here would be
1 over 240.
positive 1 over 243. Yep. So 15.2, let's bounce back there really quick and see what we didn't cover and if we need to. We looked at the second and third terms here. We looked at the 46th term, didn't we? So, sorry to change your brain, but this is worth it because then we can remember everything. You flip back to 15.2 really fast. Hopefully you can find that. We were talking yesterday about using the arithmetic mean. We just barely got into this. If you know the 2 terms, on the 2 sides of a missing term, and it's an arithmetic sequence or series, because it doesn't really matter if it goes on forever or if it ends. If I know the 2 terms beside a missing term, to find that missing term, what are we going to do? Caleb?
Well, I was gonna say you would take how many terms you've gone and divide it over. Well, have the. Okay, so I'm gonna say here. How would you say? Brian,
That's what I'm asking you.
Oh,
Ryan?
divide the change by 2.
Divide the change, so what is the change?
It's so much simpler.
I don't know, I didn't do it.
37.
Yeah, that. I tried to use fancy words and it didn't.
So we're saying 37 divided by 2?
Yep.
37's the answer. Yeah.
It's
not 37.
What's the change?
74.
Set
What? Just kidding.
What?
No, it's not.
from 15 to 59.
74 seems pretty legit.
Never mind. Wait, you could also just add them and divide by 2.
Getting there.
Sorry.
Yes, I agree. That's where we're trying to get.
44.
This change, that was way harder than it used to be, is 44. How many changes gets it from 15 to 59? 2. So we divide that by 2, and we find out that the common change is 22, which makes this 37. Now, there's an easier way to do this, actually.
You would make arithmetic mean.
Not the rude kind. What's another way that we could get 37 as our value? Rhea.
You can add 59 and 15 and get 74 divided by 2, which equals 37.
How's that easy?
Just because there's no subtraction. Gosh, Brian.
Subtractions?
So, the missing value between two terms in an arithmetic series will be the average of the values, or the mean. So, two different ways we can generate that value. This is kind of like a two-step process. This really, in my mind, is just a one-step process. Averaging is pretty easy. Here, you got to find the difference, then divide it, then add it. There's really more than 2 steps, but it's not just a straightforward add and divide. 9th and 11th terms. So we know the next door neighbors of the 10th term, because we know 9th term and 11th term. So use the arithmetic mean strategy. And if you want a formal definition, it would be a sub n equals a sub n minus 1 plus a sub n plus 1. That one's a little big. Divided by 2. If you want a formal what we're doing here. So, when I add these up, what do I get? 132 plus 98, 2 and the 8 work well together. 230. That 2 makes it 100. And I just get 230. 230 divided by 2. 115.
After what you said about series, I don't like this next question.
Right, so this is this I agree. So why this is here is kind of like guiding us to the next section. But you could hypothesize infinitely many rows. You could hypothesize an infinitely large arena. So they're not giving you an end. And they don't care about the fact that there's an end. So they're looking at this as a sequence because we don't know how many rows this has. What about row 2, row 3, row 8, row 24, row 57? We don't know how many rows there are. So that's why they give it to us as a sequence, because we don't know where the end is at. So, we know first 13 rows form an arithmetic sequence, and rows 1 and 2 are given to us. What is happening in these rows? Right? You're adding 2 seats every time. So, how do I set this up as an a sub n? The value at term n. I know we're going to need to generate the value at term 13. But the value at term n is going to be, well, we start at 14. So there's 2 different ways we can approach this. I can either use 14 and add 2. Well, I guess my parentheses should really go after the 2. It'll be nicer that way. 2 times what?
The number of seats.
Number of rows?
Yeah.
Still doesn't quite work because row 1 wouldn't come out correct.
Plus something.
Megan? minus 1 to compensate for the fact that the first row doesn't need any addition. Or, if I distributed this, it's going to give me the other way that we could write this. Start, instead of at row 0, or instead of at row 1, start at row 0. If you went one more row less than row 1, how many seats would that have? 12. And if you had distributed this and combined your like terms, so that's easier. You can get there from here, but you can really think of what would a sub 0 be, the term before my start, and then add your difference and amount of times. So we then plug in for a sub 13. 12 plus 2 times 13. So that's going to be 12 plus 26. And like David said, we get 38. So if you want to know where in the row you were, like my parents got very upset one time when they went to a James Taylor concert because they were like at the end of the row, which they thought would be good because then they don't have to like get across people to go to the restroom or
but
whatever.
they have to get up for every.
They got up for every person that wanted to come in and out of the row. And my mom was like, I can't believe these people. They won't stay seated. They don't want to watch the show. They just keep going to get popcorn and drinks. Yeah. So, strategic, when you buy your tickets, think about where do you want to sit. If you can hold it and survive the event, I would sit in the middle of the row.
Wait, but Mr. Hudson, wouldn't that kind of have like its negatives for both, like sitting in the middle or at the end?
If I know that I've got good control over my body and I'm not going to leave in the middle of the show, I'd rather sit in the middle of the row so people are going that way as opposed to coming across me. I had a friend who jokingly was like, I'll just say no. They can climb over me or something. And I was like, yeah, have fun with that.
Yeah.
I would do it.
Can we skip this, God, or are we feeling pretty good on the arithmetic?
Yeah.
Okay, so, I bet we can get through geometric really quick. I have your test to get back to. A lot of you are not finished, so I want to give you a little bit more time on that. So let's see how quickly we can get through this. And I think by 1, I want to give you guys your test back to work on.
Well, let's hurry.
I agree. So, geometric sequences are exactly the same, except now instead of a common difference, we have a common ratio. So, if you want to highlight or star or something, we now are working with a common ratio. To find that, you just take the next term divided by the current term. So, we do 6 divided by 3, we get 2. We do 12 divided by 6, we get 2. 24 divided by 12, we get 2. 48 divided by 24. We know this is a geometric sequence because all of these come out to be the same. If this was a 49 or anything other than a 48, this would not work. You can have something happen umpteen times, and if it doesn't happen one time, it's broken. So be careful. Sometimes they will trick you. They'll have it work for a few of them, and then the last one doesn't work out, especially on those state tests. They like to try to trick you like that. You'll look at a couple, be like, oh yeah, it's doubling, and then it gets skewed. So be careful. Make sure to check all of them.
So for geometric sequences, do you have to know the past term?
You have to know at least 2 terms to figure out the ratio. So whether you know the future term or the past term or whatever you know, you just need to know a next door neighbor term. Or if you're told it's geometric, and say you have the first term and the 5th term, we'll look at situations where like, how do we evaluate that? Not really.
It's his mom.
Probably is.
No, it's Amber Alert.
If you're curious, now that we've already...
It's Amber Alert.
Oh, it is an Amber Alert. Dark blue Hyundai Sonata, license plate GWS 5908. Keep a watch.
Yeah, let's all go outside now. Watch the road.
So all of your phones are blowing up wherever they are. So let's do some of these. All right. Calvin, what is the common ratio if this sequence is geometric?
For B,
Yep, for B.
it's not.
What is it?
It's arithmetic.
If people's audio's on, that's the Amber Alert.
I hate the sound. We're probably meant to be.
On the weather. Well, that's not that.
Oh, no,
So, can we define our arithmetic sequence? Please be writing this down because we want to work our skills. From exponential, I think some of us didn't practice enough because I'm getting some simple mistakes. Like the fact that a value to the 0 power equals 1, not 0. So let's be careful. Let's make sure we're writing this stuff down and turning our brains on. Just like what we just did with the stadium, the seats. If I know that I'm adding 3 every time, and I want to be able to just say plus 3n, where do I need to start? Not at 3, at 0. If I want to make a really simple... Now, can I just say 3n? Yeah. So this really turns into that my arithmetic sequence is just 3n. Because when I start at term 0 as opposed to term 1, that would have a value of 0. In C, Lynn, what do you think? If I have 3 to the 5th, 3 to the 10th, 3 to the 15th, 3 to the 20th. If I'm, and this one's a weird one because the powers. So what's another way we could write this? What would have to happen? So actually, I'm trying to decide how to ask this question. So we have 3 to the 5th, 3 to the 10th, 3 to the 15th, 3 to the 20th.
It's multiplying, but
Yeah, this one's weird, right?
Like added?
So let's rewrite this.
would it be arithmetic?
I don't know. I gotta rewrite this. I don't know.
Because you're adding 5, like, to the 5
Well, really,
power.
we're multiplying. Because remember, if the powers change, that's change in the multiplication, like how many multiples it had. Michelle?
I don't know. I thought it
Brian?
You multiplied by 243.
So, let's look at this in another form. 3 to the 10th, I could rewrite a few different ways. I could rewrite it as 3 to the 5th squared, right? Because 3 to the 5th to the 2nd power, these multiply, they'd get 10. So I could start with 3 to the 5th to the 1st, 3 to the 5th to the 3rd, 3 to the 5th to the 4th. If I rewrite them to all have that 3 to the 5th. How did you get 243?
I just did 3 divided by 5.
So what's changing here is this has another 3 to the 5th power multiplied onto it. Because 3 to the 5th to the 1st means I've got 3 to the 5th once. This means I've got 3 to the 5th twice. I've got 3 to the 5th 3 times. I've got 3 to the 5th 4 times. So every time I'm actually multiplying by 3 to the 5th. So our A1 is 3 to the 5th,
So it is geometric?
and our ratio
That was my first answer, I just didn't say it.
is 3 to the 5th. Which, when I evaluate it, is 243. Now you could also figure out what are those values, just compute them, and then look at the common ratio. But if I can write them like this, I can look at how are they changing using the exponent knowledge.
I was
Right.
thinking about it like you have like 3 times 2 times 2 times 2, however many of these you have, and then I just
Times 3 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 times 3. Yeah,
So I
exactly.
took the block that you multiplied by.
But that multiplication block is this. So we just kind of had two different thought processes. We got to the same place.
Could we get Canva today?
Because you're asking me. Yeah. Because you're not Brian.
I asked.
Every day that someone not Brian asks, will I get one?
Wait, what if that only worked if Brian hadn't asked? All right, try the got it on your own.
That's a
We
probability.
duct tape Ryan's mouth shut.
Try the
This
try the
year,
problem.
like that.
By the way, the reason they keep asking you for A1 and R, because any, and this is what's really nice, any geometric can use the explicit definition right there. Because it is your starting term times the common ratio to the power of, like how many times did this multiply. The n minus 1 compensates for the fact that the first term doesn't do that multiplication. So that's like when in the arithmetic, we looked at the situation, now it's gone, we looked at the situation where it's n minus 1 versus distributing and then just using the n. Doesn't work here. We have to use the n minus 1. I think, by the way. So, like, I can't really distribute. If I look at this,
But you could rewrite it using.
yeah, once I know what n is. But for the explicit general definition of how we're going to be able to use this, so think about the fact that in an arithmetic, let me change colors.
Well, you could do A of 0 like you did before.
Yeah, but that'd be a little funky. I guess we could. We just normally don't. Because, like, say you divide, let's wait till we see another couple examples. I'll find an example where we can talk about why that doesn't work as well.
It seems like the same thing as with the arithmetic, where you just apply the reverse process.
Yeah, so like here, we could use either of those here. So if we do it how they are used to it, we can quickly see this is geometric. Scarlett, can you tell me what the first term is? We're just looking at this.
First term.
And what is that common ratio?
Oh, it is geometric?
Yep, this one, because they're
Thought
doubling.
It was not. Okay.
So always look for, is there a consistent multiplication?
See,
So we can,
I thought if it was consistent, that meant it was not.
so arithmetic, consistent addition.
Oh,
Geometric, consistent multiplication.
okay, thank you.
You are welcome. So we can write it like this, but Calvin's arguing. Hey guys, what are you talking about?
We're talking about this.
Okay, you want to engage with us so we can all have that conversation? It might benefit all of us.
I was asking what you were so.
It's all good. It can help us. Like I'm not being like jerky teacher talk. Like I'm serious. If you have something related to this, let us all know.
That's good.
So Calvin, you want to write this in a method where I don't use n minus 1. How could we do that?
Well, if rather than using the 2 that is n or a of 1, you could reverse the process, take it to a of 0, which is 1.
So if I divide by that common ratio that I've been multiplying by, I can find this a sub 0. So then,
It would be 1 times 2 to the n, or just 2 to the n, which I like a lot.
probably you'd still want to have the 1 times in front just to show, not that it's necessary, but it shows, hey, my 0 term is 1, just to make sure people don't think you forgot to put it. You just go ahead and show, yeah, I start here and I do this that many times. So it's not necessary, but we normally still
But
keep
wouldn't
it.
that be just like given?
So yes, but Calvin's saying I could write it just like this.
Yeah.
I agree. But this clearly shows start, do, how many times. Start, do, how many times. So even though this isn't necessary, we like to leave it to show, yes, I know my 0 term or my first term, it is this value. If you want to write it like this, that's okay. I'm just saying it's a bit more clear when we write it like that.
Your shirt is really nice because you could spill ketchup or blood on it and no one would know.
Thanks,
Why would
except
we
my
get blood
pit
on
sweat
the
really easily in this one. I don't know why. It's like it holds in my heat or something. Rhea?
Well, I had a question. Don't like for the explicit formulas, do you need to know do you need n minus 1 for the explicit?
So the one we normally use is this explicit formula that's given to you on your notes. And what I was meaning, and I didn't explain this well when I was saying like it doesn't work the same way as arithmetic. In arithmetic, we like distribute and we can just simplify. This is kind of writing a whole different formula that we have to just realize without knowing an n. Wait, I can go back a term. I can back myself up, and I still know the same ratio. So it's not like we really did distribution and simplified. We just rewrote it with our knowledge. So we normally, the safe, easy way to do it is a sub 1 common ratio to the n minus 1. That's the easy, explicit way that we write geometric ratios or sequences.
Are most of geometric sequences explicit formulas or?
They can be represented by an explicit formula because it does the same thing forever.
Thank you.
You are there. So here in our geometric sequence, and we're told it's a geometric sequence, which is nice since we only see 3 of them. We know our common ratio is 3. So again, here's where we normally default to this explicit formula. If you want to use the other one, you can. But yeah, so this is one of those situations where this would then become 4/3 times 3 to the n. It's okay, you can use it. Or we go here. So Rhea, since you were asking, let's have you help me on this one. What is the first term in your sequence? And the common ratio?
Times 3.
So it's just 4 times 3 to the n minus 1.
I always get tired during the class.
Wait, so are those two the same? Are those two the same thing? Or are those two?
Yep, these are the same thing. So, I guess I'll go ahead and show this. We're not going to cover as much as I wanted to. It is okay. It's because I like taking you guys down the road of like understanding more. What happens to arithmetically combine exponents? How do we end up adding exponents together? Like if I got 4 to the 5 plus 3, which really we know would be 4 to the 8th, but how do I end up in a situation like that? Michelle?
Where you have multiple of the same term to different exponents. So like if you had a 4 to the 5th, and then you had 4 to the 3rd.
So what would have been going on between that 4 to the 5th and 4 to the 3rd? What operation?
The operation 3.
Multiplication. Because remember, when we multiply, we add the exponents. Do you see where I'm going with this?
Me?
Yeah. This is really, and I'd love for you to write this down. It's not that you have to, but this is one of those play with numbers things. This 3 to the n minus 1 can be rewritten
Which is
3 to the n times 3 to the negative 1, which is that.
I just dropped one. I'm sorry.
Just because you're just mind blown away, just it was that big of a moment,
Yeah, I
just
just
mic
got it.
drops.
I did not.
So, like with the arithmetic sequences, how we distribute and then simplify, if you want to break up this power, all you do is take the base to the n and the base to the negative 1, which then really puts it 1 over that, which becomes the simplified form, just like that. Are we clear on how we got from purple to red or blue or whichever you want to say? Well, I have lots of different colors. So, I'd rather just finish these notes, and then I'll probably just start class by giving you guys more time to work on that test tomorrow. Some of you guys, you're done and you have a grade. and some of you guys are working AO extensions, things like that. You ever? Okay, this keeps moving up. It keeps throwing it on the same page. Let's do something else. Something new page. This back will be pretty quick though. How many changes they do this a little bit of a different way. So they set up, we know the first term is 2, fourth term is negative 54. So we don't know our common ratio yet, but we do know our explicit formula. Wow. So then we can plug in, if we know the term value and we know the n value, well, if I know the term value, I have to know the n value, because what term is it? So we have our fourth term. So we plug in negative 54 equals that common ratio, or sorry, that start term of 2, common ratio to the 4 minus 1, which really, I mean, come on, we know, is going to be a
3. 2 to the third.
R. What do we do? Divide by 2. We get that R to the third.
Negative 27.
Okay, yeah, but that was the
Which
issue
is
with that
negative
question. That
3.
was about idiots. You more than idiots than I was. And you also messed up the division. And you messed up seeing a very obvious thing. Yeah, I know. We were idiots.
Hey!
No, I asked him.
You two fight like a married couple.
That's what Mrs.
Can I-
Coleman said.
Can I help with anything, or are you just bickering to bicker?
He brought up something like 3 weeks old for absolutely no reason.
Oh, it's like your homework.
Yeah, I know. See, there's no point to saying this around. You don't have to bring that up.
And just walk out of the room.
To be fair, that one can apply to both of us.
I know! It does!
To you, though, actually, for Brian, it's like 3 weeks.
Alright, so try this.
3 weeks.
If we set it up, now I know this is kind of goofy, but let's, well, so there's another way that we can do this, right? We can use the formula method that they just told us and solve it algebraically, or we can kind of just reason through it. But reasoning through it kind of does the same thing that the formula does. How many times has this ratio happened? Here, to go from 3 to 12. Twice, right? So we know that 2 times some common ratio gives us what?
12.
Whoa.
Well, I guess 9. Wait.
Ah!
Yeah,
9. Because the change here was 9. And if I just reason through this, I get that my ratio must be 4.5.
No.
How did I treat this? What mistake did I make?
Arithmetic.
This is not arithmetic.
It should be.
That would be addition.
R squared is 9.
Yeah.
So wait, how are you saying that r squared is 9? Is that, where did that come from?
No.
It's 6. I know what it is.
Nice, Davis.
So what we're really saying is
Oh.
3 times the ratio got us 12.
Yeah, he said.
R squared here really, this is not arithmetic. What difference happens between 3 and 12?
Times.
Times 4! So,
Times.
where, hey, when we set it up with the error, sorry, I took your 9 because that was perfect because I wanted to show the mistake.
How dare you?
We looked at it as if we added twice, which is 2 times whatever you're doing. But when we multiply twice, it's the ratio squared created a multiplication of 4. So that tells me that this ratio then must be,
I mean, it worked.
you're halfway there.
Oh, plug. Oh.
You don't have any other terms. You don't know if that middle term is going to end up being positive or negative. So you have two ratio options right now. So be very careful if you choose to just reason through this. Do not fall into the arithmetic trap. Your brain is going to want to do that, just like Caleb so quickly and easily. He was like, oh, 9, but you're looking at the multiplication. So get addition out of your head, or subtraction, or any of the arithmetic.
Oh, that's really cool. It's like Schrodinger's cat. Until you look
It's-
forward
yeah.
into the sequence, it's in
In
both
a
states
way,
at
it's
the
like
same
Schrodinger's
time.
cat, but that's kind of a stretch.
What's Schrodinger's left cat?
It's a thing
Yeah,
about
Brian, the
quantum
fact that you don't know that
where
says
until you
Oh.
investigate the thing, it could be in one of two states, and quantum mechanics says it's in both at the
It's
same
like how
time.
quantum computers work.
And
Because
then
you don't know
they're
until you
the two
know.
states are entangled, and then once you look, they collapse. And
It's
you will
like
see
the
state.
quantum. That's how quantum computers work. They have instead of like the
Well,
they have
the issues with quantum is that you can't
Hey.
observe it.
We need to get back on.
Yeah, I know.
So, bouncing ball, just like you did with Mr. Cabilo.
What did we do with Mr. Beal?
The bouncing
Last year, the bouncing ball
yes.
lab.
Oh, and then we were recording
We
the
didn't-
slow
So-
mo.
We didn't get to do a rude book.
If it works properly, if your ball has the right recoil, you will get heights that form a geometric sequence. And if you catch your first bounce, and then your third bounce, but you missed your second, and then we want to predict the fourth and fifth and the other bounces. Obviously, my ratio is going to be less than 1 because it's not bouncing higher. We don't have flubber. I don't even know if you guys know flubber.
Flubber. Wait.
It was an old movie. Not
Oh,
old, but
Oh, I remember it with the little green dude.
If something could bounce higher
Didn't
each
that
time,
Yeah,
would it create infinite energy?
Yeah.
yes,
Brian,
that was like
that-
flubber. Go watch it if you've never seen it.
And-
Watch it
and
over
it's
spring break.
going to-
Rent it from the library. I'm sure they have it.
I was
All right. So, what we're seeing here, hey, just like the situation above, we've had this common multiplication times r. We see that r squared. How do I figure out what that equals? Up there, we could have done 12 divided by 4, or sorry, 12 divided by 3 to get the 4. We are now at this value, having started from this value. If up there we did the further term, I don't like saying bigger, the further term divided by the earlier term, we do the same thing here. We get 49/100ths, which actually works out really easy. Because they are nice numbers, they're both perfect squares. And remember, when we square root a fraction, we square root the numerator and denominator separately, and this comes out to be 7/10. So each bounce is 7/10 or 70% of the previous. So we write this as my a sub n. I can easily start with first bounce times 0.7 to the n minus 1. Or if we evaluate this so we can just have a power of n, you figured it out yet?
Oh.
Figured that was your favorite method, so you would just keep doing those. So this would put 0.7 in the numerator, or sorry, in the denominator, and flip it. So this will become
Would it be 1,000 over 7?
100 times 0.7n times 1 over 7/10. So if you do 100
Yeah,
divided by
1,000
7/10.
1,000 over 7.
Yeah, okay, so what is that?
A bad number.
So this is one of those situations where this is easier to leave it that way. Because we could do this, but it's not nicer. Does that make sense? Why a lot of times we can just stick with the explicit, it's easy enough. Cool? And
Geometric mean.
I think we could probably do this.
And I remember, oh, that.
So, I'm going to skip the reasoning. If you read through that and you get confused, then come see me. But what are the possible values for the missing term in the geometric sequence here? We already kind of discussed this a little bit. Since we only have two terms shown, plus or minus, we don't know if that middle term has a positive or negative value. And I know that it's going to be between 48 and 3. So I just multiply my 48 and my 3 together, then I take the square root because I know, well, what's 48 times 3? 120 plus 144.
But didn't we do a different geometric mean last year?
I mean, this would be like if you had
The thing where you set up the two
48.
fractions. Yeah, we did that.
This is that.
Oh, yeah.
12 would be your answer here. So, but positive or negative actually, because either of these could be. If it's negative, they're both negative. This is not your ratio. This is the value. So if you just want to find the value in the middle and you don't really care about the ratio, or you can then figure out the ratio later, use geometric mean and that will find that middle term. That is all the time we have for today. So this homework is evens or odds, so please write that on here when you get it. Evens or odds, or you can write like half or 50% or whatever. Helps you remember that. Evens or odds.
Okay, remember over the summer when you just had to do half weights in general? So you picked the easiest one, and then I had to do.
Yeah, I was explicit about that this year, saying the expectation for homework is half, evens or odds, your choice.
I have a question.
Yes.
So, I'm still gonna get a sweatshirt for the t-shirt design.
Should be. I have been hands off of that for a little while, but you should. Yeah.
I just want to make sure you guys are
I finished one day.
No, that's they know.
2
that
days
too
because
is
you said I
merged
finished this
design.
day before the last day. And you
Don't
finished
quote
the
me,
second
'cause
day.